All right, so it's a pleasure to have Atul back here after, I guess, how many years now? 4 years, 5 years? I mean, when did
Four
you
years,
take
I
the
think,
quantum
four
field
and a
theory
half.
course? I think it's 5 years, yeah.
Yeah.
So,
Yeah.
so I think he's going to tell us about light transforms and celestial holography. Let's see what he has to say. Yeah, go on, Atul.
Thanks for inviting me, guys. Of course, it would have been at some point. I'll come back to Bangalore to visit. Yeah, I'll make up for this. Anyway, I want to talk about some of the stuff related to scattering amplitudes and flat space holography that I've been working on in the last year or so. This talk happens to be based on a solo paper, which I seem to have forgotten to mention here, but from July or something. Okay, so the first half of the talk will be sort of a broad overview of the subject anyway. And in the latter half of the talk, I'll try to give some concrete punchlines about how to relate amplitudes to conformal field theory type objects. But even historically, over the last 20 or in fact, last 50 or so years, we have begun to sort of get an understanding, a much better understanding of scattering amplitudes, which has superseded the usage of things like Feynman diagrams. So over the last 20 or so years, beginning with the work of Witten in 2003, we've sort of developed what you could roughly in a generalized sense call dualities, where you never actually compute scattering amplitudes using Feynman diagrams anymore. You either use something called on-shell methods, which are BCFW recursion, on-shell recursions based on locality and unitarity, or if you're somewhat more fancy, you use topological strings in fancy spaces like twistor spaces, which give you worldsheet formally for loads of amplitudes in maximally supersymmetric Yang-Mills and gravitational type theories. I want to discuss a new sort of duality that has been popping up on the horizon over the last 5 or so years. One of the characteristics of these older dualities that people have developed, these first two kinds of dualities, is that they don't have a notion of strong-weak duality. Either you don't have a notion of any change in coupling, or you have something that gives you a weak coupling duality between a theory on something called twistor space and a theory on space-time. But none of these have a flavor like ADS-CHEP-th, where you would want to have a strong coupling theory on a smaller dimensional space being dual to the gravitational theory in flat space. So people have started looking at this, and the latest incarnation of this idea is called celestial holography. The idea is basically to have a two-dimensional theory that lives on the celestial sphere, which is basically, you can think of it as the night sky, but the night sky in momentum space, if you're being completely rigorous. So the conjecture is that there is going to be a two-dimensional theory living on our celestial sphere, which will somehow holographically encode the physics of quantum gravity, presumably, but at least perturbative quantum gravity and perturbative gauge theory in our four-dimensional flat space. So this is, of course, the next natural thing to do after you study ADS-CHEP-th before you go to any actual cosmological spacetimes. You start studying holography in flat space. And this is natural from the viewpoint of scattering amplitudes, because scattering amplitudes are the natural holographic observables of quantum gravity, even in ADS. So I just wanted to start with giving you a mention of the kinds of evidence, some circumstantial type evidence that people have amassed over the last 10 years for why such a two-dimensional holographic dual to four-dimensional quantum gravity should exist. The classic evidence towards this direction is the duality, is the equivalence of the four-dimensional Lorentz group and the two-dimensional conformal group of the celestial sphere. So this basically says that if you do a Lorentz transformation in the bulk of space-time, and you take your Lorentz parameters and see how they act at null infinity on the celestial sphere, then they act in a conformal way, which intuitively is saying that if you move towards the celestial sphere in a boosted frame, the celestial sphere still stays spherical. it never turns into an ellipse if you're moving in a spaceship too fast. So this is, of course, a classic thing, and everyone knows that. Say from the analysis of embedding space formalisms for CFTs and stuff like that. But there's more. People have also more abstractly studied asymptotic symmetries of gauge theory and gravity. And they've realized that something akin to what happens in ADS3, if you choose the boundary conditions of your gauge parameters carefully, or your diffeomorphism parameters, you can show that asymptotically you get symmetries that contain a copy of two-dimensional Virasoro. Plus, there's a classic BMS story where you go to asymptotic infinity and Poincaré gets enhanced to super translations plus rotations. Recent work by Strominger and friends, which I did not want to cite all the papers, so here are some reviews, shows that BMS, the rotation part of BMS gets enhanced even further to the Virasoro algebra. So there's a secret 2D Virasoro algebra that lives at null infinity, and you could hope to build a two-dimensional theory that sort of makes it dynamical. Now, there's a similar story for asymptotic symmetries of gauge theories. And these, if you study them carefully, the large gauge symmetries act like two-dimensional Kac-Moody symmetries on celestial sphere. So all of these are somewhat kinematical statements. The real sort of beginning of a dynamical statement comes from the observation that soft theorems in 4-dimension in the bulk can be rewritten so as to look like two-dimensional CFT word identities. And so I'm not going to write down the expressions, but just the intuition is that they look like two-dimensional word identities of some conformal field theory living on the celestial sphere. It so happens that the leading Weinberg soft photon or soft gluon theorems look like word identities of such a 2D Kac-Moody symmetry. And there's a similar story where there's a certain subleading soft theorem, which you can rewrite, you can parameterize to look like a two-dimensional Virasoro word identity. And there's loads more evidence that you could probably
Atul, can I clarify something about this picture? Yeah. Can you hear me? Yeah. Can I ask a question?
Yeah.
Yeah. So as you said that the celestial sphere is essentially in momentum space, right? I mean, the celestial coordinates are a way of rewriting the 4-dimensional momentum, right?
Yeah.
So the picture on the right, are we supposed to think that there is a Fourier transform version of the celestial sphere which gives us this momentum space celestial sphere?
Yeah, so this is basically simply going to be that I'm going to deal with amplitudes in momentum space. And then I'll just parameterize this. I'll write down a specific stereographic coordinate on the celestial sphere in terms of the momentum components. So in that sense, this will be precisely a celestial sphere in momentum space. I'll show you the expression in a bit.
Okay. Yeah, but the picture that you've drawn on the right, that is supposed to be, I'm supposed to think of it in position space, right? I mean,
I've
so
drawn
how
it
are
in
these two things
position
connected?
space, yeah.
Yeah.
Well, this is at the moment just pictorial. The precise version of it lives in momentum space. This is just meant to be a cartoon.
Okay.
You could think of it, you could think of it as particle. If you think of these things as particles traveling on null geodesics, then you can think of the null geodesic as depicting a direction of a null momentum as depicting a direction along a null geodesic. And that direction is the asymptotic point at which the particle will head.
I see.
Yeah.
Okay, thanks.
Thanks for the question. Okay, so just to give you some motivations for why you should study such a program. The main thing is that you could probably try to find much better ways of doing perturbative quantum field theory using such a celestial CFT if it existed. Because amplitudes have always been holographic objects, at least, because they naturally map some data for some free limit of the theory or at past null infinity or some past Cauchy surface. up forward to some final states at future null infinity. So amplitudes always only seem to depend on data at past and future null infinity, but it just so happened that all our virtual processes and our ways of drawing Feynman diagrams seem to require a bulk from us. So it's a natural question to ask if we could just find some mathematics that lives at initial and final null infinities that somehow reproduces these scattering amplitudes without ever talking about the bulk. And if such a mathematics could be discovered, and if in particular it's a conformal field theory, then you could use many new techniques. For example, you could try to bootstrap. So there's a standard thing in the amplitudes literature where they try to bootstrap amplitudes using locality, generalized unitarity, and things like that, which is something called the S-matrix bootstrap, and analyticity, famously. One could dream, at least, that S-matrix bootstrap might be secretly related to a two-dimensional conformal bootstrap. Of course, at the end of the day, one would want to go beyond perturbative QFT and one would want to find, well, firstly, one would want to find a perturbative UV completion of gravity. And this might be represented as some sort of strong coupling physics on the boundary conformal field theory. And of course, at the end of the day, one would like to go beyond perturbation theory, try to find a strong weak duality, and maybe turn the 2D CFT on its head and use it to study some strong coupling physics in the law. There are loads of applications and dreams and fantasies that motivate one to study such a two-dimensional dual. But there are also many issues.
I had one question. So is it a priori obvious that in flat space holography is a strong weak duality?
It's known at the moment, but sort of indications are coming up, and I might mention one in my second to last slide.
That it is indeed strong weak.
No, indications that it could be constructed from a stringy duality. So one would hope that at the end of the day, that would give some strong weak duality. I don't know at the moment of a specific coupling that you could invert, but there are indications that there is a string theory that you could try to do holography with.
So, but my question is basically there should also be a theory that is defined independently, sort of on the boundary, right? So you know, you might have from the bulk. Somehow you would imagine that the macroscopic bulk description would be somehow the weak gravity description or the weak string coupling description. Yeah. But the dual theory, what it would be is in some sense the question. The question or
strongly coupled.
Yeah. Okay. Yeah. Anyways, I'll wait.
So we don't have any indications of what the dual theory is at the moment, but we know that there are stringy descriptions of the bulk of gravity and these twisted string type things that I just mentioned. And we hope that there might be some concrete holographic duality on twisted space. But I'll mention it in the second to last slide if I still have time. I put it at the end because that's the most conjectural thing. Okay, so there are many issues to tackle.
Can I just follow up on that question? So, do people want to think of, when we talk about four-dimensional bulk and S2, do people want to somehow think of this S2 as related to the string worldsheet?
Well, I'm gonna. No, that's not the case. The analogous thing would probably be this ADS3 CFT2 story, where you have the worldsheet, which maybe there's a map that takes the worldsheet and covers the S2. There's some sort of an analogous story in the twisted string business. At least that's what I want to think of it as. But not the worldsheet itself, but some sort of thing that maps the worldsheet into the celestial sphere, but to some higher degree or something like that.
I see.
There are some people who want to think of the celestial sphere as a worldsheet, but they haven't amassed too much evidence yet. I think there's a group in Northeastern, Stiebergen, Taylor, and friends. But anyway, don't know much about it. So there are many issues to tackle that you guys mentioned. The main issue being that There's no explicit construction, so we don't know whether this is a strong weak duality or whether it even exists at the moment. There's just circumstantial evidence, loads of it, but still circumstantial. And there are the current sort of formulation that I'll discuss in a bit has a few problems that one would like to overcome. So just to give you an idea of the kind of problems we're going to encounter, there are the naive counting of the spectrum. Since we're going from 4 dimensions down to 2 dimensions, but this 2-dimensional CFT supposedly has to contain states that are in one-to-one correspondence with states of massless quantum field theory. I'm only going to discuss pure Yang-Mills and pure gravity in this talk. I'm not going to talk about massive particles. If it's supposed to have states that are in correspondence with massless particles, then massless particles depend on 3 sort of degrees of freedom. Any null momentum in 4 dimensions has 3 degrees of freedom. You can think of 2 degrees of freedom as giving you a point on the celestial sphere, as I sort of pointed out to Aninda's question. There's a 3rd continuous degree of freedom that sort of gives uncountably many, so 1 continuous degree of freedom to all of these operators. At the moment, we don't have a generating spectrum or any idea of finding a generating set of operators that generates a spectrum of this 2-dimensional CFT. Since we have uncountably many states, we don't have any understanding of unitarity. We don't have any understanding of unitarity. Oops. What did I do?
We can still hear you. I think your picture is, your picture has frozen for some reason, but I can see your pointer and I can hear you.
Can you hear us? I think he has.
You might have.
Aninda, can you hear me?
Yes.
Okay.
Yeah, you're back.
Atul, can you hear us?
I'm sorry, that was a Wi-Fi problem on my side, I think. My DRAM stopped, so I had to change. Let me share again. Oh, it's already shared. Maybe you can restart recording.
You can hear us, right?
Yeah. Can you not hear me?
We can. Yeah, please go ahead. Yeah.
Can you hear
me?
Me?
See the screen also. Screen, everything is fine.
Sorry about that. Okay. So there are some issues which have to do with the spectrum of states. There are some interesting issues that have to do with 2-dimensional unitarity. Don't have an understanding of unitarity bounds or anything in the celestial CFT at the moment. You don't have any understanding of what the central charge is. So loads of open questions that people like, all the CFT people like you can try to work. One question that I want to talk about today is actually a very basic question. The correlation, in the simplest naive form of the conjecture that I'll discuss, the correlation functions will look like they're actually distributional because secretly there will be scattering amplitudes at heart and they will come with some momentum conserving delta function type objects. And I'm going to talk about something called the light transform, which is going to solve this problem and give rise to and map scattering amplitudes to objects that have some power law behavior of standard CFT correlation functions. So this is the first sort of fully functional prescription that we've been able to come up with to actually make scattering amplitudes look like standard CFT correlators, which will be the punchline of the talk.
Yeah, sorry, okay. I missed something very basic. Can I just ask you something? So, what are the evidences that this thing that you're going to talk about is actually a CFT?
Oh, all these asymptotic symmetries that seem to have a copy of Virasoro in it. And yeah, the CFT side has the evidence comes from the existence of Virasoro. Yeah.
Virasoro, okay.
And then there are Kac-Moody's, and also you get an evidence that there's richer symmetry structures. It's just saying that the CFT comes from the gravitational.
But your third point says that we don't really know whether it's a unitary CFT or something more exotic.
Yeah. So we don't have any idea of what the central charge is.
Uh-huh.
Yeah. These are some of the
And
main
also,
big issues.
I think if it is not clear that it is unitary, then it's sort of less clear whether you know. So basically, I think those questions become somewhat more serious, right? I mean, if you just have symmetry, is it clear that it should be a field theory? You know, you basically have it should be. All it's really saying is it is a conformal theory. And I mean, I'm not saying unit. We ultimately expect it to be unitary. I agree with that. I think in the like I think it is a conservative assumption, but at the same time, if you are maybe there is a way to characterize a unitary theory by in some other it's not clear that because the objects that you're looking at are not necessarily they are some sort of objects which are transformed from scattering amplitudes, right?
But Chetan, isn't it more interesting if this theory wasn't unitary and then we needed to find out what rules actually give rise to four-dimensional unitarity, bulk unitarity? I mean, I think that's a more interesting question.
I'm just saying that it's not clear what the notion of time evolution fundamentally description, because it is living somehow on the asymptotic boundary, right? So unlike in the case of ADS-CFT where there is a well-defined time evolution, so here it is more like you have a Hilbert space, and maybe operators, but it's not so much like you have a good notion of unitarity preserving time evolution. That seems a little. It's always struck me as somewhat odd about this flat space holography. So I'm just saying that, like, you have a statement about symmetries, but in the sense, I mean, the flat space that argument, but it has never completely. I was not clearly able to follow like whether there is a real statement about Hilbert space time evolution, etc., in this boundary theory, which is kind of conventional. Yeah. Anyway, I think I think we understand.
I see. Yeah. Maybe. Yeah.
You're
We should.
perfectly right. It's not clear that it's a quantum mechanical theory in the standard sense at the moment, but that's why you have to study it, I guess. Okay, sorry. Let me just quickly give you a summary. So I'll go through an overview of momentum space scattering amplitudes, spinor helicity formalism. Then I'll tell you the conjectural 2D CFT correlators that we build from these momentum space amplitudes. That will involve something called some type of a some Mellin transform. And then I'll describe how the celestial amplitudes, which will initially appear to be somewhat distributional, can be turned into much more CFT correlator looking objects by doing something called a light transform. And now I don't think I'll have time, but maybe I'll try to discuss their relation to twistors at the end of the day. So there will be a diagram which will show that light transforms are secretly related to twistor amplitudes in twistor space by the same kind of Mellin transform business. In any case, let's sort of start with the actual meat of the talk. So recall that in flat space, the scattering of massless particles can be parameterized in terms of spinor helicity variables. So you take a null momentum and you write it in components, and then you write it as a 2x2 matrix. The standard thing to do is to write this as this linear combination, which you can construct in terms of Pauli sigma matrices and stuff. And note that this matrix has determinant 0. So you can see that this is P0 squared minus P3 squared minus P1 squared minus P2 squared. The determinant is 0 precisely when the momentum is null, so that you can break it apart into two spinor type objects. You can write it as a tensor of a pair of spinors, lambda and lambda bar. And explicitly, here's some intuition. You can parameterize lambda and lambda bar through some stereographic type coordinates, some objects z and z bar, which look like stereographic coordinates on the celestial sphere in momentum space. And the scalings of these lambda and lambda bars are sort of only fixed up to an overall scaling. So the product of the scale of lambda with the scale of lambda bar can be fixed in terms of this component P0 plus P3, but U and U bar are not completely fixed by this. This means that there is some redundancy in this description, and this is called little group scaling redundancy, by which it just means that if you write P alpha alpha dot as a product of a spinner and its conjugate, then you can also rewrite it as a product of some number times the spinner times the inverse of that number times its conjugate. And it so happens that the scattering amplitudes have this little group scaling property. They're not actually invariant under this little group scaling. They scale with the power that depends on the helicity of the particle. So positive helicity gluons of helicity +1, positive helicity gravitons of helicity +2, things like that. But whenever you compute an actual cross section, all of these dependencies drop out because you take a mod square, and in Lorentzian signature, you take this T to be a pure phase. Okay. So I was hoping people have seen these kinds of things before, but if anyone has a question, feel free to ask. Okay. Then we can move on. Some examples. We have the 2 gluon amplitude. Now at 2 points at tree level, you only have the identity part of the S matrix, so you usually forget about this. But this is basically just a standard delta function on Lorentz invariant massless phase space, that kind of object. For n gluon, for an amplitude of n gluons, the simplest amplitude, the simplest non-vanishing tree level amplitude happens to be an amplitude which has 2 negative helicity gluons and n-2 positive helicity gluons. So stripping off all the dependence on color factors and traces, the real juice of the amplitude is contained in this thing called the Park-Taylor formula. This consists of a combination, a Lorentz invariant combination of the momenta, which are constructed out of the spinor helicity variables by these determinant type bilinears. So angle bracket ij is basically the determinant of the 2 spinor lambda j and the 2 spinor lambda I arranged in a 2x2 matrix. And you can evaluate this in components, and that looks like Zij. And there's your familiar momentum conserving delta function, which you usually don't write when you write scattering amplitudes, but the expectation in celestial holography is that this delta function will also emerge through some celestial dual, so you want it to be there. Okay. Now, what are celestial amplitudes? What we want to do is we want to start with these momentum space amplitudes, and we want to convert them into some objects that transform conformally covariantly with respect to the little z's and the little z bars that parameterize the spinor helicity variables. So you want to think of z's and z bars as coordinates, stereographic coordinates on a celestial sphere. And we want to, what we're going to do is we're going to do a Mellin transform. So take the momentum space amplitude, fix the little group redundancy that I mentioned about by fixing the scalings of the 2 spinners to be given in terms of the energy of the particle, roughly speaking. So you can fix this scalings to be given by the square root of some positive omega, and the other thing has a scaling square root of some positive omega and times a sign, which tells you whether the momentum is past pointing or future pointing as a null vector. And then you have a dependence on the z's and the z bars, which, as I showed you, are just p1 plus I, p2, or p0 plus p3, and its complex conjugate. So once you parameterize your states like this, you fix your little group scaling. Now you can try to do some manipulations on this, and the manipulation that gives you a conformally covariant object is this Mellin transform. You integrate out in all these, you integrate out all these frequencies from 0 to infinity, all these energy omegas, and that gives you something that transforms like 2D Euclidean CFT correlators living on the celestial sphere. So this should be a familiar Möbius transformation law, which maps these curly A's will transform under these Möbius transformations like AZ plus B, CZ plus D, and so on, like the standard conformal correlation function transformation. Okay, any questions about this definition? This is sort of the most natural thing to do that people have come up with. Okay. And the idea is to conjecture that these objects, these amplitudes that naturally live at null infinity and naturally transform as 2D CFT correlators are actually 2D CFT correlators. And a conjecture will be that there will be a bulk, R13, and there will be a CFT living on some abstract celestial sphere. And okay, you can formulate this conjecture directly in terms of momentum eigenstates. You can say that the momentum eigenstates map to some operators, but any such operator will not transform conformally covariantly with respect to the celestial sphere conformal group. That's why you work with boost eigenstates, which are related to these momentum eigenstates with the Mellin transform that I showed on the previous slide. And now you can conjecture that there are these boost eigenstates that are related to certain conjectural operators O labeled by the sign, whether the momentum is incoming or outgoing, a conformal dimension delta, which at the moment, as I was mentioning earlier, is a continuous parameter. We don't have any idea of how to constrain a generating set of operators that generate all these general operators with generic weight delta. But as a means of experimentation, you can just take this to be a parameter that you can tune, and a spin j, which is a helicity j, which is just the bulk helicity particle. And of course, this will be dependent on z and z bar, which will be our points on the celestial sphere. And the holographic dictionary that we posit is that the celestial amplitude will be a conformal correlation function of n of these operators that depend on the helicities and the conformal weights appropriately. Okay. So some examples of this, of course, are warranted. The two-gluon amplitude is the easiest thing. You can do the Mellin transform fairly easily because you can localize it on some of the momentum conserving delta functions that I showed you. And this just turns into a delta function that sort of conserves what is called total boost weight, something similar to how momentum space amplitudes conserve total translation charge, the sum of all momenta. Here you get a conservation of total boost weight, or what you could think of as dilatation weight, delta 1 plus delta 2 minus 2. And the non-trivial part, okay. And then there's the obvious thing that one particle has to be incoming and the other has to be outgoing at 2 points. And the only interesting dependence here is that Z12 have to be completely coincident. So as you see, this 2-point amplitude, it doesn't look like a CFT correlator at all because it has this weird distributional dependence. But it so happens that you can actually do conformal transformations. And because of the presence of this delta function, you can still write the transformation of this thing as a conformal transformation. Something similar happens at 3 points. You get something that is not naively looking like a CFT correlator, but the generic properties of the amplitudes, Lorentz invariance and stuff guarantee that it will transform in a 2D conformally covariant way, because it has to be Lorentz invariant in the 4D sense, and the 4D Lorentz transformations are secretly 2D conformal transformations. Now, the 3-gluon amplitude is only non-zero in 2-2 signature. It's 0 in 3-1 signature because it contains a pair of delta functions that set z bar 13 and z bar 23 to 0, but z bar 13 is equal to z13 in Lorentzian reality conditions. The two kinds of spinors are conjugate to each other. So setting z bar 13 and z bar 23 to 0 would also mean to set z12, z23, and z31 to 0. So even though it's not clearly obvious that this amplitude is 0, you can show that the momentum space amplitude, that this is the Mellin transform of the 0 in 1-3 signature. That's why it seems that at least at the level of...
I had a question. So, so you're somehow, it's basically you're bothered about the delta functions because they don't look like conformal correlation functions. That's the point, right? And also,
yes.
What about these theta functions? They also seem to be somehow extraneous to the standard CFT type of structure, right? Are they problematic or no?
They're not that. They are not problematic in the sense that they're not proper distributions, the like finite objects. So all they do is give you amplitudes, like break the amplitude into different channels. So for example, you'll have some scattering channels where 1 and 2 have to be incoming. So, well, at the level of this 2-point thing, it's easier to see. You can write this delta function that sets one incoming and the other outgoing as a theta function. So it's only setting a kinematic channel constraint.
Yeah, but
it's not something
is the channel constraint, can you think of it somehow as a consequence of some signature choice, or is there some way to think of that? Because for instance, if it is, these are not, you don't expect the form of the, even in CFT, when you go to Lorentzian signature, it's not just these, the powers of Z1, 2, Z2, 3, and Z3, 1, right? I mean, you have extra stuff. So can you think of these extra things and somehow a feature that you might expect in non-Euclidean signature? Because it's what you mentioned about channels.
You mean the...
No, not the delta functions necessarily, but the thetas and maybe the delta function. Delta, it's not delta that you had in the 2 blue 1 amplitude.
Okay, so no, in standard Lorentzian CFT, you do not see, I mean, whether it's Euclidean or no, they're not there. Basically, because these any standard Lorentzian CFT doesn't have this notion of this extra parameter.
Right, but this is 2-2 signature, right? But this is 2-2 signature. That's what I was asking you about. Yeah,
I'll actually mention in a moment how precisely these things are 2-2 signature analogs of conformal correlators, and these signs will actually transform non-trivially under conformal transformations. So this is not a standard Lorentzian 2D CFT. Yes. And at least I haven't seen an example of such an object other than this.
Thanks.
Hello. Hello. So I had a small question. Is it possible to have a mathematical relation that labels the boost eigenstates in terms of the conformal dimension? So how do you label?
The boost eigenstates are already precisely labeled in terms of these conformal dimensions. Yeah.
No, I mean, is there a mathematical relation like that, or is it just a state itself like that?
Is it just a name you mean? No, it's so you could. You have to take the angular momentum generators and construct a weird linear combination that looks like M12 plus I M03 plus I times M12 minus I times M03, which turns into an L0 type Virasoro generator on the celestial sphere. And this diagonalizes, so you get a weight delta plus J over 2 with respect to that weird generator, and so on. You can construct L0 bar in terms of the other ones.
So it does diagonalize it, right?
Okay. Yeah. You can write down these L0 and L0 bars in terms of bulk angular momentum, and you get delta plus J over 2. Okay, I haven't never sort of done it myself. I just know how to write down the generators, but I believe, that the wave functions do diagonalize. It's not that hard to believe, Okay, the point is that these are highly distributional, and I'm going to give you a prescription to do some extra transforms that map these correlators to other objects that still look like conformal correlators in 2-2 signature. And they will not have any kinematic delta functions. Unfortunately, I don't have a way to get rid of these delta functions in the weights, but they're just a part of life at the moment, yes. And the theta functions, as I said, are not that big of a trouble. We don't even understand what kind of trouble they are at the moment. Okay, so now we want to go to R22. So R22 has recently been named Klein space in some work by Strominger. So if you want to adopt this name, feel free to adopt a child or a name, a puppy. Okay, so the idea to go to R22 at the most basic level is that you turn a minus into a plus. So you want to study null momenta. A null momentum in Minkowski space satisfies this quadratic constraint. To go to R22, you perform a Wick rotation. And the nicest thing to do happens to be to Wick rotate P2 into -I times P2. So firstly, this turns the constraint into a constraint given by a quadratic form of signature 2, 2. And now you can write the stereographic coordinates as well. So here you start with the stereographic coordinates and you do the Wick rotation. They turn into real coordinates. They're no longer stereographic coordinates on a celestial sphere, but as I'll show you probably on the next slide, they're real coordinates on a torus. Okay. And the reason I Wick rotated P2 was because there was an IP2 in my conventions here, but you could Wick rotate any other P as well. So the nice thing about 2-2 signature in comparison to Minkowski space is that in Minkowski space, lambda and lambda bar were complex conjugate spinors up to a sign, depending on your choice of a little bit of scaling. And they were dependent on each other, like lambda bar was the conjugate of lambda. In 2-2 signature, they're actually independent real spinors. So this allows you to study amplitudes as analytic or real analytic objects with not completely analytic, but you can study the lambda dependent behavior separately from the lambda bar dependent behavior, and it allows you to access a lot more singularities and stuff like that in 2-2 signature. So this is not, gosh.
Something went wrong.
I think his internet connection went.
Yeah, you're saying something about edit on.
Yes.
Wi-Fi issues. I have no idea why these are happening today. Sorry, guys. Is my screen still shared?
Yep.
Okay, great. So as I was saying, you can go to 2-2 signature and you can treat Z and Z bar as real and independent variables. And then study the analyticity and other kind of properties of amplitudes. So these have been in usage for quite a while, but they were in the study of scattering amplitudes, but they've now started appearing in the celestial holography program because they allow you to sort of not worry about them being related to each other and treat these delta functions that I showed you on the previous slide as independent real delta functions. So you could try to do stuff with them that you couldn't do in Corinth signature, where these delta functions would make the whole amplitude vanish. Now their Z bars are independent from the Z's, so this doesn't necessarily have to vanish. Okay, so I suppose I should take the opportunity to cite CHEP-th because he's invited me to a talk. So here's some little.
It has nothing to do with the 2-2 signature that you're talking about, though. Thank you anyway.
Effort toward that. No, that's okay. It's a nice generalization, isn't it? Yeah.
Nice.
So the idea here is as follows. You have the conform R22 actually looks like a big triangle. It's not that harder to draw a conformal diagram for R22 than just Minkowski space. But there's a very big difference. Conformal infinity for R22 is a connected object. So, or you could think of it as saying that the light cone of any point in the interior is also has only one huge connected component. This is different from R13, where you have two components, which are, well, maybe connect two disconnected components of null infinity, where you could think of one component, the past null infinity, as the place where past states live, and future null infinity as where the future states live, and you could try to construct some scattering maps. Here you will have, rigorously speaking, you'll have a problem for defining scattering. What we're going to do is we're just going to define scattering amplitudes by analytic continuation, study them as some objects defined on this, and we'll study them as some objects that live on the conformal bound, on the sort of analog of the celestial sphere, the sort of fibers over this boundary. So that analog happens to be not a sphere any longer, but a torus. So Oh, yeah, topologically, if you want to think about R22, the conformal compactification of R22 looks like S2 times S2. And when you go to the boundary, the sky, if you were living in R22, looks like an S1 times S1 embedded in S2 times S2, I think equatorially or something like that. So this S1 times S1 is your sky now. You want to build a theory that lives here. And you can think of it, of course, it's a torus. You can open it up. You can think of it as a patch with the opposite edges identified. In terms of the sort of coordinates I mentioned earlier, you get a picture like this, where if you start with a metric on R22, you can get an asymptotic metric on this celestial torus, which is a Lorentzian signature, 1,1 metric. So in some appropriate type analog of stereographic coordinates, this metric just looks like dz times dz bar, but z and z bar are real coordinates. So this is a Lorentzian 1,1 signature metric. And in these coordinates don't cover the whole celestial torus. They happen to cover just a patch. And there are two Poincare patches that I've shaded with respect to this Lorentzian structure. One patch, there are two patches. They're sort of symmetrically placed. I've just been able to display one patch as a connect component, but these four triangles also joined together by the identifications of the edges. And this has a pair of null geodesics which you can study. The null geodesics corresponding to such a metric are basically just the diagonal lines. So there's a line that goes along Z and there's a line that goes along Z bar. And keep these null geodesics in mind. They'll be what allows us to define light transforms on the coming slides. Now, you can't study scattering in a conventional sense. So the sort of rough, somewhat of a bad idea, but it's just a rough idea that allows you to write down expressions that you can sort of analytically continue back to Minkowski signature, is to just break this null infinity up by hand. This breaking is not Lorentz invariant, not 2-2 signature Lorentz invariant. You can actually take points on this half of the null infinity and find Lorentz transformations that map it to here. But modulo this issue, it so happens that this issue doesn't pose a big issue when you're just analytically continuing 1,3 objects to 2,2 objects. You can just write them down as Lorentz invariant objects, or Lorentz covariant objects. And I'll show you on the next slide precisely how this is done. Modulo this little issue, you can just break this apart, and just to get some intuition, you can think of this is only just an intuition. You can think of placing some initial states on this half of null infinity, and these somehow evolve into some states on the final half. And in this celestial torus picture, what will happen is a state that lives on the interior of this this darkly shaded diamond will actually evolve into a state that now lives on the exterior, this slightly shaded diamond. This slide is just to give you some intuition for the kind of world we're living in, but nothing too important. The important thing is all about the kinematics of Z and Z bar. We want to construct some analog of celestial amplitudes. So what we do is we take 3 1-signature amplitudes and we analytically continue. Once we analytically continue them to do 2-signature, they give you objects. Even at 3 points, they give you objects that are non-zero, as I mentioned earlier, because those delta functions that were making the 3-point amplitude vanish now don't impose the vanishing of both Z's and Z bars. Once you work with such a heuristic, you can do the same Mellin transform and construct some objects that transform covariantly into 2-signature. Again, you take the same decomposition of the spin-Helmsley variables. It's just that now Z's and Z bars are real and independent to each other. Now you get something that transforms like a 1 plus 1 dimensional Lorentzian CHEP-th correlator. But you get some stark differences from the Euclidean CHEP-th case. Firstly, these objects are all real now. So you'll get some absolute values here. rather than, yeah. And the much worse difference that I was mentioning earlier in response to Chetan's question is that these signs, epsilon i's, that sort of telling you whether a state was incoming or outgoing in Lorentzian signature, once you analytically continue to 2-2 signature, they're not Lorentz invariant any longer. This is an instantiation of the problem that incoming states and outgoing states are not well defined. You can make, as I was saying, you can map points on the incoming part of null infinity to outgoing part of null infinity. So these epsilon i's are not invariant under 2-2 signature Lorentz transformations. And this is the only sort of difference from a standard Lorentzian CFT that we will encounter. Our correlators will depend on an extra parameter, epsilon, which will transform non-trivially. So we'll have to account for this when we sort of write down our correlator in terms of some conformally covariant structures. This will happen automatically. Any questions about this? This is sort of the deepest subtlety at the level of my talk, at least. Calculational subtlety. Now you can ask me after I show you examples, I guess. So, okay. Now that we have this, now that I've set out this machinery for you, I want to talk about something called the light transform, which will help us make the celestial amplitudes non-distributional. Sorry, I don't even know whether I mentioned that I'm going to call these objects celestial amplitudes. Yeah, these are called celestial amplitudes in the literature because they, quote unquote, live on the celestial sphere or celestial torus in this case. We want to make them non-distributional. The trick is to find some integral transformations of the celestial amplitude that preserve conformal covariance, but absorb those delta functions. And Lorentzian CFT does give us such nice integral transformations. The idea is that there are integral transformations that are induced from the Weil group of the conformal group SO2, 2. And these map one representation of SO2, 2 to another representation. I'm going to use the transformations that are called light transforms. These map representations of weight delta and spin j into representations of weight 1 minus j and spin 1 minus delta. You can't have arbitrary spin in 2D Euclidean CFT, but when you study 1 plus 1D Lorentzian, you can sort of make sense of this in an analytically in the sense of analytic continuation. So these are not local operators in the CFT. They have to be treated as sort of extended operators. But when you apply them to celestial amplitudes, you get objects that look very much like 3-point correlation functions of local operators. So at the moment, that's their most interesting application. So how do you define such a light transform, such an integral transform? You take your original operators that were dual to boost eigenstates. So an operator, say, of weight delta, spin j, and some sign epsilon. And you integrate it along a choice of null geodesic. So suppose we integrate it along the null geodesic, along which z bar is kept constant. So we integrate in z, letting the integration parameter be z prime. And then there's a little measure factor, z mod z prime minus z to some power, that ensures that this whole thing transforms with these weights and spins. So it changes the transformation law in z. You have to be slightly careful now to sort of transform the sign as well, because you know that in the Lorentz transformation, the sign is going to transform, and the transformation law looks something like this.
Is it fair to think of this as like an effort to basically identify what are the true local operators of your CFT2, CFT 1,1?
I would very much like to think of it like that, but I'm very scared about. Yeah, so I would like to compute the higher point CFT correlators first. At the moment, I have computed the 2- and 3-point light transform correlators. and they all look very much like nice CFT correlators of local operators. And but I don't know how the higher point correlators will, strictly speaking, behave. Maybe they will have some indications of non-locality hiding in them when you maybe try to do some conformal block expansion of a 4-point light transform.
In the boost basis, you said that it's only the low point correlators which have those delta functions, right? Okay.
Yeah. And that's what I wanted to, that's basically the main application here. These light transform integrals will absorb those. At higher points, you don't have any delta functions. You can't localize the light transform integrals. So you get some complicated hypergeometric functions. And at the moment, I'm trying to do this at 4 points and see what the answer looks like, basically. So the main takeaway from this slide is that you can define these objects. These still transform as conformal primaries of this complicated 1 plus 1D CFT, where you think of conformal primary in the generalized sense that you transform Z and Z bar, but you also transform this little sign parameter in the appropriate way. And if you do this correct transformation, the transformation of this sign of Z prime minus Z in the denominator and everything ensures that the full light transformed operator transforms with the conformal weight delta and spin 1 minus, conformal weight 1 minus J and spin 1 minus delta. Similarly, there's a conjugate encodes light transform where you can integrate along the Z equals constant null geodesic. Okay, so these are different from the standard light transforms that I used previously in my paper. So the light transforms that we had been using until now were sort of directly taken from the literature on Lorentzian CFT by Kravchuk, Stephens, and other friends. But I recently realized that you could slightly modify it with these moduluses and these signs to make it fully conformally covariant. And in today's talk, I'm going to just mention sort of slightly better 3-point correlators that come out. So more or less, this is based on my work from July, but there are some elements of work in progress here, but not too much. Okay, feel free to ask me about that at the end of the talk if you like. There are some, so by now there are many places where these light transforms have popped up. It's not just what I'm going to talk about. So the first place where they popped up was in a paper by the Harvard group on the conformal block expansion of a 4-point celestial amplitude. I think they took the case of scalar fields, massless scalars. So it turns out that if you take a 4-point celestial amplitude with all its weird singularities, even the 4-point one has some delta functions that I didn't display for you, but it also has a delta function. You sort of break it apart, and it naturally breaks into conformal block exchanges over some discrete modes, which you can think of as some soft exchanges, and a continuum, but a continuum of light transform modes. So this is where the light transform first popped out. And today I'm going to talk to you about the application that they can render all the 2, 3, and 4-point celestial amplitudes non-distributional by absorbing all those bad-looking delta functions. They also seem to be very useful for understanding the symmetries associated to celestial CFT. So the global symmetries that are induced from asymptotic symmetries in the bulk, they seem to be, the generators seem to want to be the light transforms of soft gluons rather than the soft gluons themselves. And this is secretly, my sort of claim is that this is secretly related to Penrose's twistor theory. And I'll mention how light transforms can actually be recast as some transforms that take you to twistor space. I'm actually not going to mention it now because I'm going to be over time now. But let me just cover this.
You can take half an hour more if you need. Feel free to.
Let me cover the main application, then you can ask me questions and then we can see, I guess.
Okay, see.
Yeah. So how do you tame the delta functions? The idea is you want to construct new bases you want to construct the same basis. You want to keep your basis consistent. You don't want to do different transforms on different celestial amplitudes to make them non-distribution. So what you do is you take as your basis the L light transformed positive helicity particles and the L bar light transformed negative helicity particles. Once you work with this basis, all celestial amplitudes become non-distributional in one go. You don't have to keep changing your basis now. So to give an example of how this is done, the celestial amplitude is computed by a pair of integrals acting on this 2-point celestial amplitude. So now my delta functions are real and independent. So I've written them like that. Here it's fairly easy. Sorry, I should have written these delta functions should now be delta of z1 minus z2 prime here. Sorry about that. I just copied this from the previous slide. And this delta function should be z bar 1 prime minus z bar 2. So these delta functions can be used to localize these two light transform integrals. This is the easy bit. You quickly get a non-distributional answer. You could do the other thing as well. You could have light transformed the negative helicity particles in the z bars, in the z's, and the positive helicity particles in the z bars, and you would still have gotten a nice power law behavior. But this is the only prescription that also works for 3-point amplitudes. So as I said earlier, just to be clear, I don't yet know how to absorb this delta function that conserves boost weight, but I know how to get the standard CHEP-th power law in terms of the kinematic positions on the celestial tours. And this step function is still going to be there, but all it tells you is which kinematic channel that one particle has to be incoming and the other particle has to be outgoing. It's just that this is now slightly different from the original delta function because it now slightly depends on a new kind of conformal invariant object. You can show that under the light transform conformal transformations law, this combination of momenta is invariant. The sign of this object is invariant, so the theta function is invariant. So this is what I was mentioning when I said that you get slightly more complicated dependence on this extra parameter, and this is different from a standard Lorentzian CHEP-th, where you wouldn't have such a parameter. Okay. The main meat of the prescription is at 3 points, where you can take your 3-point celestial amplitude. Again, you replace z1 bar by z1 bar prime, and similarly, and you integrate along z1 bar prime, z2 bar prime, and z3 prime. So in the positive helicity particle, you integrate along z, and the negative helicity particles, you integrate along z bars. And you recall that this 3-point amplitude has a pair of real now delta functions that localize the z bar 1 and z bar 2 integrals trivially. So now your delta functions go away, and you have a nice conformally covariant power law form of the 3-point coordinator. The third integral here is a non-trivial integral, but you can turn it into an integral over a 4-point cross ratio. So once you've localized the z1 bar and z2 bar prime integrals, you get 4 points in your problem, z1, z2, z3, and z3 prime. So you can rewrite this third integral as an integral over a cross ratio of these 4 points. And you can do this. This is a fairly simple conformal integral that I haven't written down, but the answer is fairly concise. You get, now in a generic conformal integral, again, the difference from standard 1+1D Lorentzian CHEP-th, in a generic conformal integral will only depend on some numbers. It wouldn't depend on these kinematic positions anymore. But because there's no cross ratio constructed out of just z1, z2, z3, and you're integrating out the only cross ratio in the form. But in this celestial CHEP-th, you have these signs, these objects, these ratios of signs that are conformally invariant. So your normalization can actually still have some step function type dependence on these signs. So modulo this mildly richer structure that you find in celestial CHEP-th, the rest of the structure is the same as the usual Lorentzian CHEP-th, where you have some OPE data, and this OPE data happens to be some beta functions. And all of this occurs as a normalization of this 3-point amplitude. You get some extra factor of science when you evaluate the third integral from some Jacobian type object, but this product of science is also conformally invariant. That's fairly straightforward to show. Okay. Any questions about this?
Yeah.
This is what allows us to.
Because you're taking the light transform, the usual conformal dimension gets replaced by some combination of spin, and the spin gets replaced by the conformal dimension.
Yeah.
So this would be interpreted as the 3-point function in some fictitious CFT where spin is continuous.
At the moment, yes. I don't have a way to interpret this object as a correlation function of a bunch of local operators. But the hope is not that, the main reason why I would like to do this is not to find new local operators, but to get some objects that have straightforward CFT power law dependence so that you could study their OPE data. So for example, the next thing that I'm going to try to do, and I think other people are also doing this, is to take a 4-point light transformed amplitude and try to do a conform block expansion and try to get it to divide in terms of these standard looking 3-point amplitudes. This is very hard to do in the original thing, which are these delta functions. It's not clear how to take a 4-point celestial amplitude, take an OPE limit and reduce it to a 3-gluon celestial amplitude. That's still unproven. But now that we have standard power law forms, there is no excuse for us not to have a proof that it works. And if it doesn't work, then celestial CFT doesn't exist. Okay, so that's the next thing we'll do. Or I'll try to do, but somebody will probably get to it before me. Okay, let me quickly tell you about twisters. This is not, you can feel free to turn off your heads if that was the main punchline of the talk, that there's now a way to get non-distributional answers. The same thing will work at 4 points as well, because at 4 points, one only has one delta function. So one can absorb it in 100 different ways. It's only the 3-point thing that was sort of somewhat non-trivial and required precisely this prescription of light transforms. But now I want to tell you that, light transforms are related to twisters. So how do you introduce twisters? I'm going to introduce a real version of twisters by starting with your spinor helicity variables, lambda and lambda bar, which are now both real and independent to spinors, and Fourier transforming in the lambda bars. So the idea of twistor theory is basically that a twister is a half Fourier conjugate of the spinor variable. So it's a Fourier conjugate of lambda bar. So a twister is just lambda, the 4-component object with the first 2 components being lambda and the second 2 components being mu, which is obtained by doing a Fourier transform. And now you can try to write amplitudes in the basis of such states that are labeled by lambda and mu. Such states are obtained from a Fourier transform of the momentum eigenstate. And you could posit that there are going to be some operators in the dual CFT. These will again not be conformal primary, but they will be obtained from some conjectural operators that are dual to momentum eigenstates by a Fourier transform in lambda bar. The nice thing about twisters is that they turn little group scaling into an overall scaling. So now little group scaling of lambda and lambda bar behaves like an overall scaling on the twister eigenstate. So whenever you have a state that has this label by twistor z, if you rescale its twister by a non-zero real parameter r, then the state scales like r to the minus 2j over 2. It has an overall scaling. And similarly, at the level of scattering amplitudes, if you write amplitudes, if you take usual momentum space amplitudes, do these Fourier transforms, then little group scalings will be turned into scaling, overall scalings of these twisters. So these twisters naturally live in real projective free space. Okay. You can relate. It so happens that light transforms have a secret dual life. They're actually twisters. or they're at least related to twistors by the natural operation that takes a twistor eigenstate and turns it into a conformal primary state. So firstly, you want to find this operation. You take mu and lambda, and now you use this overall little group scaling redundancy to fix scale. And the easiest, sort of quickest way to fix scale is to fix the first component of lambda to be 1. And the second component of lambda can be z something. And then you have mu alpha dot. You can set the overall scaling of mu alpha dot to be some positive number omega times some sine epsilon, which is a priori unrelated to the momentum space objects. And you can set the first component to be 1, the second component to be some other independent real number z bar. So this is a scale fixing that's completely analogous to the little group scale fixing in momentum space. Once you've done this, you can take this positive number omega and you can integrate the twistor eigenstate to turn it into a conformal primary on the Lorentzian celestial CHEP-th. And this is where the light transforms pop up, because there can't be too many such integral transforms that give you new conformal primary states. So it so happens that this conformal primary state that you construct out twistor eigenstates can be written as some sort of somewhat slightly complicated, but just a two-term linear combination of the light transforms. And geometrically, what's happening here, this was suggested to me by Strominger in one of the conferences, actually. This was his realization, so to speak. Geometrically, what's happening here is that you can light transform either on this part of the null geodesic on the celestial torus or the other half of the null geodesic. If you notice, this is only half the null geodesic. This is not a full null geodesic that's circling around the full torus. If you do transform along the full null geodesic, the full geodesic looks something like this. It goes like this, then comes here, ends here. Since these two boundaries are identified, it starts here, ends here, and goes along the torus and comes here. So secretly what's happening is that the transformed twistor space is giving you a light transform that's continued along the full null geodesic rather than just one half of it. It just so happens that each of these light transforms are conformally covariant by themselves, so you can just use the light transforms as a basis for states rather than using the twistor objects. And but otherwise, it so happens that these two objects are closely related by such a diagram. You can take away such a diagram from this slide. You take momentum eigenstates, you can Mellin transform them to boost eigenstates, and you can light transform to get something which you could call light ray states or whatever you like. But you could obtain such light ray states, or at least such a two-term linear combination of light ray states by going the twistor route. Now the question is, what does the twistor route accomplish for you? Does it unravel something new for you? And it sort of kind of is beginning to do that. The twistors have only started to appear in this program. And I'm going to give an intro to twistors talk in the Celestial Holography conference next week. So you can tune into that if you want to hear more about twistors. But here's a basic motivation for how they appear. So the symmetries of celestial CHEP-th can be thought of as global symmetries.
One quick question. So
yeah, sorry, this was.
Yeah, so I mean, so this construction is really tied to the 2,2 signature and the real twistors, right?
That is very true. Yes, real. Yeah, exactly.
So for instance, I mean, is there there is this, the transform that you said Witten 03 whatever, that one, is that the one where he you know, the like there is a, you know, the famous paper, right, in which you know,
yeah,
like,
they started all of it. Yeah, basically.
Yeah, so sort of. And so that doesn't have a generalization to the full complex twistor space, does it? I'm just asking because it is, you know, I've not kept track of this at all.
That's okay. This is exactly. So this Fourier transformation only works in 2-2 signature.
Yeah.
And there is a generalization to complex twistors and to complex projective free space, but that doesn't go through this. That goes to something called it's called a complexification. But yeah, that doesn't tell you much. But you can actually first go to C4 rather than R22. You can study C4, complex projective force, complex dimensional force space. And then you can study, well, not exactly a Fourier transform, but something called an incidence relations that allow you to take C4 into CP3.
That's the twister that I'm familiar with. That's what that's the
Oh,
one
you're
that
familiar with that. Okay.
I mean, familiar in the sense just, I don't know about, this, that would give you something more like CP3, right? It would be a CP1 on a CP3 or something like that. Here it is. That's, yeah, okay. Anyway, I just wanted to kind of place where all these things lie into the landscape of twistors, So go ahead. Anyway.
This is a sort of real equatorial slice of that CP3, actually, intuitively.
I see. Thanks.
And all the RP1s that are lines in this real twistor space are the real equatorial slice of the CP1s there. Yeah. But this is easier to present. I don't want to confuse my audience. So that's keeping it real. Keeping it real.
Yeah, go ahead.
Any other questions about, I realize that this is the least familiar thing. So if there are any other questions from the grad students or anyone else, I'm happy to take them about twistors. Okay, coming back to CFT then. The symmetries of celestial CFT, if it is a CFT, should be parametrizable in terms of invariances of the operator algebra. So firstly, you have to find a way. So what I'm going to tell you is that twistors can be applied to the study of these symmetries. But first, let me tell you how you get these symmetries, how you formulate them. So the operator algebra of celestial CFT is formulated in terms of collinear limits in the bulk. The sort of conjecture here is that scattering amplitudes have fairly well-defined collinear limits in which they factorize. So these are just two particle factorization channels. If you study, say, particle 1 and particle 2 becoming collinear, then the momentum associated to this internal propagator goes on shell. Now, if you write down the Mandelstam P1 plus P2 squared, it's proportional to Z12 times Z bar 12. That's fairly easy to show. Because of this, the limit when P1 plus P2 goes on shell is the same as either Z12 going to 0 or Z bar 12 going to 0. And in the dual celestial CFT, this looks like an OPE limit of the correlation functions that reproduce celestial amplitudes. So with this kind of a conjecture, you can basically study collinear limits of scattering amplitudes in the boost eigenstate basis, and then postulate that those will be the operator algebra of my celestial CFT, and then try to see what the symmetries of this operator algebra are. So until now, I've done the gluon amplitudes. I haven't shown you graviton amplitudes, but just for the sake of symmetries, the graviton case is more fun, so let me try to do that. The OPE of two positive helicity outgoing graviton states. So I'm just going to label them as G subscript delta 1. I'm not going to call them OJ delta, just for simplicity. G delta 1 is a positive helicity graviton. If you construct the collinear limit of a pair of such operators, if you construct the collinear limit where these two particles are positive helicity gravitons, then you get from that an OPE for these two dual operators that looks something like this in the boost eigenstate basis. Contains a bunch of Euler beta functions, but other than that, these are just anti-holomorphic descendants, conformal descendants of G delta 1 plus delta. So it contains a conformal primary which has weights delta 1 plus delta 2 plus its anti-holomorphic conformal descendants. And this part of the OP is only constructed. This is the singular term in Z12. I haven't written down any terms that are non-singular in Z12. So this part, the singular part of the OPE, is actually invariant under the action of conformally soft gravitons. So what you can do is you can find a subalgebra of this OPE whose action which you can view as a set of Kac-Moody currents. And you can show that this OPE is associative with respect to the OPE of those Kac-Moody currents with two of these G's. So that says that the OPE is invariant under symmetries generated by those currents. So these currents are integer weight objects. You take some weight, delta equals 2 minus k, where k is going to be a positive integer, 0, 1, 2, 3, so on. You take G delta and you take a residue. Now, if you want the OPE of such a current, W with G, the prescription is that you take a residue at delta equals 2 minus k in this OPE. So in this case, you take a residue of delta 1 at some integer 2 minus k, and you get the residue from the gamma function that's contained inside this beta function to give you some fairly simple differential operator. That residue sort of truncates after a while. You only get finitely many terms, which you can reassemble into a nice product of differential operators form. So this really behaves like some Kac-Moody current, albeit with slight polynomial dependence in Z1 bar, which you can sort of expand out, get component currents. This behaves like these soft gravitons behave like Kac-Moody currents acting on the hard gravitons G delta through such a differential operator. And you can prove, did I not cite? Yes. It was proven in this paper, in which Payton Singh, that when you act with W on such a pair, then the OPE is left invariant by the action of these. So they do generate a symmetry. Now, this is an infinite dimensional symmetry algebra because K runs from 0, 1, 2, 3, and so on over all positive integers. So is there some natural, can we identify this with some classical symmetry algebra in standard literature? And indeed we can. This is secretly a copy of W1 plus infinity. Some sort of symplectic diffeomorphisms of a two-plane. And the real way to see this is through twistors. So the real way to identify what these symmetries are is through a twistorial picture. So just to recap, the chain of transforms that take you to the twistor eigenstate. If you start with the conformal primary eigenstate, in terms of which I've written the OPE on the previous slide, you can do inverse Mellin transforms to get some sort of an OPE for momentum eigenstate. And then you can do a Fourier transform to get an OPE for these non-conformal primary twistor eigenstate dual operators. You could write this at least, irrespective of whether they exist or not. You could try writing this out, what the OPE looks like in terms of these non-conformal primary states. And the OPE drastically simplifies. This is some of the magic of twistors, that they simplify extremely complicated things into extremely simple geometric objects. So in terms of a particular scale fixing, the kind of scale fixing that I showed you on the previous slide, you can fix the first component of lambda to be 1, the second component to be some affine coordinate lambda. Mu alpha dot you can keep as 2 arbitrary components. You can write this OPE between a current, a soft graviton current WK, and a twistor eigenstate of a positive LSD graviton. And that complicated looking differential operator collapses to a linear differential operator in the mu's. And this differential operator, moreover, acts through a Poisson bracket in mu's. So this twistor eigenstate is a function of lambda and mu. And this symmetry generator now acts through the Poisson bracket of a specific Hamiltonian, this combination of mu's, which, as I said earlier, is slightly dependent on Z bar, but you can expand it in Z bar and get component Hamiltonians. The Poisson bracket of this Hamiltonian with G of lambda mu. But this Poisson bracket only depends on mu naught and mu 1. It only differentiates along the mu directions. So it's a two-dimensional symplectic form. And this clarifies the symplectic origin of these symmetries, these soft graviton symmetries. It tells us that these WK act as canonical transformations of the two plane of mu naught dot and mu 1 dot that sits not in momentum space, not on the celestial sphere, but in twistor space. So this actually tells you, this is really giving a hint as to where these symmetries are coming from. And indeed, there's a natural symmetry structure, at least in self-dual Yang-Mills and self-dual gravity, where you do have W1 plus infinity acting as non-trivial symmetries of self-dual gravity. And the current expectation is that global symmetries of self-dual gravity might still persist as asymptotic symmetries in the full theory, or at least in this celestial CHEP-th. And that's what these soft gravitons are somehow making manifest. Now, again, as an application of light transforms, so quite neat application, you can sort of take this non-conformal primary twistor eigenstate, do the Mellin transform, turn it into a conformal primary, and the resulting OPE looks like the OPE of a pair of conformal primaries, but it now again acts as a linear differential operator in contrast to the extremely complicated order k-1 differential operator that I showed you on the last slide. So you could presumably hope to use such a linear differential operator type symmetry to maybe constrain celestial OPE in the future. Maybe this gives more credence to the fact that the light transforms of these operators might be the correct local operators secretly, and some maybe with respect to a different conformal group or some more exotic object. But at the moment, this is just a fun application, and hopefully this will have some actual computational usage, converting everything to a linear differential operator. But this also sort of fits into a bigger picture where one could hope to get celestial CHEP-th actually as a holographic statement in twistor space. If twistor space is acting as such a fundamental means to unravel symmetries, maybe it can also act as a means to unravel the full celestial CHEP-th, not just its soft sector. And there is some buildup of evidence towards such a possibility in recent work. Just to give you an overview, the idea is to start with twistor strings and do holography for twistor strings, where twistor space, just intuitively, is a patch of CP3, which covers almost all of CP3, which is topologically R4 times S2. And the idea here is that CP3 is the complex twistor space, some sort of complex version of the real RP3 twistor space that I showed you. The details are not important. But on this complex 3-manifold, you put some theory. To be precise, you put some topological B model plus some instanton stuff. But you put some theory on this complex 3-fold, which you can restrict to this patch, R4 times S2, and compactify along S2. And it's known that there are certain theories which you can compactify along S2 on such a twistor space to get Yang-Mills and gravity, or at least perturbative Yang-Mills and perturbative general relativity on space-time. And these theories come from twistor strings. And so the hope is that there is not a duality, but some sort of a celestial triality between a 6D space, a 4D space, and a 2D space, where celestial holography is just going to be the completion of this commutative diagram. And the actual meat of the duality will be a holographic duality between twistor strings on this complex 3-fold and possibly some D-branes wrapped on this S2 factor. So there are some hints of this that are starting to emerge in some recent work, mainly in this third work by Kevin Costello and Natalie Paquette. And hopefully this will go somewhere. We'll probably find out in a few months. Okay, just to conclude, there are loads of future directions. The subject is still in its infancy. One has to find a generating set for the spectrum. One has to find the celestial OPE, maybe through conformal block expansion techniques. Now that we have non-distributional celestial amplitudes, even though they look like non-distributional correlators of some non-local operators, nevertheless, as soon as we have something that looks like standard CHEP-th correlators, we can try to apply conformal block expansion techniques to it and try to see whether the 4-point amplitude decomposes in a consistent way with the 3-point OPE coefficients. Then the next thing is to classify, the big open problem is to classify symmetries of quantum gravity in flat space and quantum gauge theory. And here by symmetries, I mean asymptotic symmetries of the global symmetries of the celestial duo. These will of course be much richer than the actual global symmetries of quantum gravity in the bulk. Okay, and then there are some ideas as to build a probably toy model for celestial holography for self-dual subsectors. And as I mentioned on the previous slide, connect with ideas of twisted holography for twisted strings that have been developed by Costello and Piquet and other friends. But yeah, all of these are still ongoing. There's loads of ongoing work at the moment. And hopefully this program will settle down in the next 10 years and we'll have some really cool celestial duo. Okay, I'm open to questions, but feel free to leave. It's already too late if you want to grab your evening coffee or something.
So are there any questions? I think we asked him enough questions anyway during the talk.
Thanks for that. Yes, I enjoyed it.
All right. So if there are no further questions, let's thank Atul for this very nice talk.
So one question. So
oh yeah,
is there a hint that flat space holography can be more useful in describing quantum gravity than ADS holography?
To understand quantum gravity in flat space. Yes.
Yeah. Okay. So our world is basically
hopefully in the same sense that n equals 4 helps you understand, or maybe some people would even say define quantum gravity in ADS.
Okay. Okay. Thank you. Thanks.